Alright, so we already talked about how to solve systems graphically, but now we're going to use a process called substitution, which means you don't have to do any graphing. You can just kind of do it by using those equations, manipulating them, and using some algebra. So name, date, title, and let's get after it. For a warm-up, I want to consider this problem. It says evaluate y minus 2x plus xy when x equals 3 and y equals negative 2. Now this should be a familiar sort of problem. We've seen problems like this before. Hopefully they strike you as pretty easy to understand and to conquer. So we know that we have an algebraic expression here that they want us to consider, and these algebraic expressions have variables which could have different values, but they're telling us what variables that they're concerned with. So whenever we have y, to evaluate this, we'll plug in whatever y is, whatever value they gave us for y every time we see a y. So instead of y minus 2x, it'll be negative 2 minus 2 times whatever they said x is, and in this case it's 3. And then instead of plus xy, we'll plug in 3 for x and negative 2 for y. Now we can just use our order of operations, and it'll be negative 2 minus 6 plus negative 6. And I'll play add-offs here because I think it makes sense. So we have negative 2 and 6 more negatives and 6 more negatives. So that'd be 8 negatives and 6 more negatives, which would be 14 negatives. Now what I want to point out here is that we knew exactly what to do, and the idea was we just said, well, if x equals 3, then I can replace x with 3. When you're drawing on the idea that equivalence or equal signs tell us that things are interchangeable. So equivalence has to do with interchangeability, and in fact it means interchangeability. So let's look at the notes. When two expressions are equal, they are interchangeable. So just what we were just describing. So if x equals something, then we can replace x with it. The solution to a system of equations is where both variables have the same values for both equations. So what does that mean? It means if we're looking at, maybe there's one linear equation and there's another. If we're looking at the solution to that, we know it's the intersection point. It is the only point where they have the same x and the same y. So over any of these other points, I could go to any other x value and we'd have a positive y value over here, a negative one over there. But this is the only place where the x value gives us the same y for both equations. That's going to be important to us as we look at this process. So here's the process. It says to solve a system using substitution, solve one equation for a variable. So just find out what is the variable equal to. We just want to get the variable alone. X equals or y equals. Step 2, plug in the equivalent expression. So whatever x or y is equal to, we're going to plug that in whenever we see x or y in the other equation. And then we'll just have an equation with one variable. So we've replaced that variable that we solved for, and we can solve an equation that just has one variable. We're going to solve that. We're going to find out what the variable is equal to, whichever is left over. And finally, we're going to use that variable value, so whatever we solved for, whatever we found x or y to be, we can use that to find the other variable. That sounds so confusing, but it makes sense when you see it in practice, so let's check out number 1. This says, solve using substitution, and the two equations are 2y equals 6x minus 10 and negative 3y equals x minus 15. Step number 1 we said is to solve one equation for a variable. We just want to find out just what is y equal to or what is x equal to. So let's think, what are some pretty easy ones to replace or to get by themselves? So let's try and get y by itself, and that will be a good step up here. We could also get x by itself by just adding 15 to both sides, but I like the idea of getting y by itself. Divide the left side by 2, so I divide the entire right side by 2. And we have y equals 3x minus 5. Now step number 2 says we'll plug in the equivalent expression. We're going to take this and say that's what y is. That's what y is equal to, so it's interchangeable. And I see a y over here. So I can replace these two things that are equal with one another. And the reason I can do that between two equations is because the point that we're concerned with, even though these are different lines, the point that we're concerned with is where the y's and the x's are the same. They intersect at a point where the coordinate pairs are the same. So we're allowed to do this. And that's the reason it makes sense for it being the intersection. Now I'm going to replace, and we're going to see why is this useful. Why is it beneficial? Well, now we have negative 3, and instead of y, I'll plug in what y is equal to. It's equal to 3x minus 5. Now continue writing that second equation, equals x minus 15. Why is this useful? Well, now I just have an equation with one variable. And if I have an equation with one variable, I can find the value of that variable that makes it true just using some nifty algebra and equation solving steps. Make sure you distribute that negative sign. We have x minus 15. I see that I have a positive x on the right and negative x's on the left, so I want to collect positive x's. That's what I usually think about. Add 9x to both sides. Let's collect the constants, the 15 units. Let's put those to the left. On the opposite side, we're trying to find out how many units or what constant is x equal to. So we have 30 on the left. Our negative 9x and positive 9x canceled out. We have 10x on the right. Our negative 15 and positive 15 canceled out. I can divide both these by 10. And we're going to get that x has to be equal to 3. So for when these are both equivalent and interchangeable, x is equal to 3. Well, if x is equal to 3, and I know that's the coordinate where they cross, that's the x value where they cross, well, how am I going to find the y value? Which equation do I plug it in? Well, if they're crossing, it doesn't matter. They cross at the exact same point, the exact same y value. So I can plug in 3 for x to either one of those equations. I'll plug it right into the first one. So 2y, actually, and because I changed around this equation in a valid way, I made an equivalent equation that just looks different, I can plug it into this one even. So I'll say y is equal to 3 times x, and in this case we're wondering, what about when x is 3? 3 times 3 minus 5, y would be equal to 9 minus 5, y would be equal to 4. So I know that these two lines are going to, oh, that's a minus sign. These two lines are going to cross at the point 3, 4. That's exactly where they'll cross. That's the only point they have in common. That's an ordered pair that makes them both true. So I can see if I plug this ordered pair into both, does it make them both true? 6 times 3 minus 10. 6 times 3 is 18 minus 10 is 8. Is 2 times 4 8? Yes. Alright, plug in x for this one. 3 minus 15, that'd be negative 12. Is negative 3 times 4 negative 12? It is. Alright, this is the correct solution. Let's check another one. Don't be scared. But this is a tough word problem. I want to show you how to use substitution here. Margie is responsible for buying a week's supply of food for dogs and cats at a local shelter. The food for each dog costs twice as much as food for a cat. She needs to feed 164 cats and 24 dogs. Her budget is $4,240. How much can Margie spend on dog food? So let's just go through and let's just try and find some equations. What do we know? Well, we know from this sentence that the food for each dog, and I forgot some words, the food for each dog food costs twice as much as cat food. Now what else do we know? She needs to feed 164 cats and 24 dogs. So she needs to do 164 times the price of cat food, and she needs to do $24 or 24 dogs times the price of dog food. And we know that when she spends, or however much she spends on dogs, when she spends all that money, her total cost is going to be $4,240. Now, this looks pretty annoying. What can we do? Well, it does look kind of annoying with these big numbers, but it also looks primed for substitution because I already have D isolated. So I can plug in D. I can plug in 2C for D because I know that they're equivalent. So 164C plus 24, and I won't multiply 24 times D anymore. I know D is the same as 2C equals 4,240. Okay, we can also, I'm going to do this real quick. 24 times 2C, 24 times 2 times C is the same as 48 times C. Okay, if we have 48C and 164C, we're going to have 212C is equal to 4,240. Divide both sides by 212. Oh, this is going to work out neatly. 212. So the reason it's going to work out neatly is because if you multiply 212 by 2, you get 424, but it's in the tens place, so we need to multiply by 20. So she gets to buy 20 packages of cat food. Well then, how much can Margie spend on dog food? Or she's going to spend $20 on cats, on each cat. Sorry. Yeah, she's going to spend $20 on each cat. She spends $20 on each cat. How much is she going to spend on each dog? D is equal to 2 times how much she spends on cats. So she's going to spend $40 per dog. And how many dogs are there? 24 dogs. 24 dogs times $40 each is going to give us 4 times 24 would be 96. Again, it's in the tens place. $960. She gets to pay $960 on dog food. Whew, there we go. That was a heck of a problem. Hopefully you stayed with it. Probably the word problems we'll use for substitution will be maybe a little simpler than that. Won't have as many extra steps. But hopefully the substitution process is still making sense. The fact that if we know what D is equal to, we can plug in that other expression for D. It doesn't just have to be a regular value. So let's leave you with 2 practice problems to solve on your own. The first one is a system that's already laid out for you in equation form. The second one, I'm going to ask you to use this word problem, a little simpler than the last, but you're going to have to write your own equations, and then you'll solve it using substitution. A test has 20 questions worth 100 points, so 20 total questions equals 100 points. The test consists of true-false questions worth 3 points each, and multiple choice questions worth 11 points each. How many multiple choice questions are on the test? All right, so that first sentence gives you part of what you'll need for both equations. So best of luck. I'll see you later.